Hello everyone, welcome to Physics 1 Lab 1 Constant Velocity. My name is Xin Sun and let's get started. So here are the basic contents of this presentation. Firstly, I'm going to talk about the introduction of this lab, including the goals, key concepts and assumptions, as well as force analysis on the Scotch tape, which is the system in the force analysis. Then I will show the tracker analysis, which is also the observed experiment of a Scotch tape moving constant velocity. I will also demonstrate computational modeling using GlowScript to generate the predicted model based on initial velocity, position, and zero net force while using iteration. In this case, a while loop to plot a graph of position versus time of the motion. I will then discuss results and differences of both observed and predicted experiments, and meanwhile, I will focus on potential errors caused while doing this lab. Last but not least, I will address some essential problems if we take a step further to rethink about this experiment. Alright, so let's fast forward to our first part, introduction. The purpose of this lab is to apply Newton's first and second law to constant velocity motion of an object and compare experimental results using tracker analysis with theoretical or computational results using GlowScript. The core physics concepts that we used in this lab were Newton's first law, which describes the relationship between a physical object and the forces acting upon it. We also utilized Newton's second law, the momentum principle, to generate velocity and position update formulas. The velocity update formula says that the final velocity is the addition of initial velocity and net force over mass times delta t, where delta t in this case is a relatively small time interval. Most importantly, since this lab is all about constant velocity, the net force, as we assume, is zero. Another important formula that we used in this lab was the position update formula. The final position is the addition of the initial position and the average velocity times delta t. This formula helped us plot the position of the moving tape on the graph. The key assumptions that we made in this lab include ignoring air resistance and friction force. We also assumed that the tape was moving in a straight direction along x-axis. Here's the force analysis. The system in this lab is the Scotch tape, and the surroundings are basically everything else, including the ground, air, earth, and my hand. When my hand touched the tape, there were three forces acted on the tape: normal force, gravity, and the force in the direction of the motion. At this time period, the tape was accelerating because of non-zero net force. As there were only two main forces which cancel out each other exerted on the tape was moving at a constant velocity. The following is my tracker analysis. We can see that the FPS is 30 per second, thus delta t is 1 over 30 seconds. The tape's mass is 0.045 kilograms and its diameter is 0.054 meters. The total time of observation of constant velocity motion is 1.6 seconds. As I defined the right direction to be the positive x-axis, the tape was moving toward the negative x-axis. The initial position of tape is 000 meters, and the initial velocity generated by the first two positions is negative 0.33600 meters per second. Okay, so here's my computational modeling on GlowScript. The first few lines are basically the attributes of the tape that I stated before. Then I apply Newton's first and second law for the iteration part. Notice that the while loop time is smaller than 1.6 seconds, which is the observation time. In this lab, we assume that the net force is 000 Newton, which is the same for every iteration. Hence, using Newton's second law update velocity and position formulas, I added the slight change in position during every delta t while keeping the v average equals to v initial. Here are the graphs generated by the predicted model. You can also find the project details by clicking the link below. So I plotted the experimental and theoretical results in Excel and discovered some differences and possible errors of my experiment. Notice that the green line, which is the experimental line, is flatter than the purple one, which is the computational line. As we can see, at first, the graphs are really similar and the two lines overlap each other. As time progresses, they differ because of friction force and air resistance, which is in the opposite direction exerted on the tape to decrease the magnitude of the velocity. The differences could be caused by some errors. For example, the tape could be moving toward a different direction. Also, there are slight differences between the center of mass plotted in tracker. The frames recording the constant velocity motion could also be inaccurate, and there might be rounding errors while calculating. What if we flip the x-axis to positive since the tape was moving toward the negative x-axis? So I think the difference is just reflecting the plotted results along x-axis like the graph below. Since we assume that the net force acted on the tape is 0, is it possible for us to say how many forces are added together to give 0 net force in this case that we observed? Well, I'm confident to say that the normal force and gravity cancel out. However, based on the slope of observed motion, there's friction force or air resistance which act in the opposite direction of motion that slows down the velocity, thus it's not possible. This is the end of my presentation and thanks for listening.